We can hardly imagine daily life without electricity. Do you know how current is generated from this hydroelectric power station? Ørsted's discovery showed that we can produce a magnetic field via an electric current. What will happen when a bar magnet is moved inside a copper coil with several turns? In 1831, Faraday found that a moving magnet inside a coil can generate electric current. It allows us to convert mechanical energy into electricity. Faraday made a solenoid of a large number of turns of copper wire. And connected the ends of the wire to a galvanometer. There is a deflection towards the right in the galvanometer when the bar magnet is inserted into the coil. There is a deflection in the galvanometer towards the left when the bar magnet is removed from the coil. No current is induced when the magnet is at rest near the coil. EMF is induced only when there is relative movement between the magnetic flux and the conductor. Faraday concluded that a current was induced in the coil owing to a change in the magnetic flux passing through the solenoid. Magnetic flux is the number of magnetic lines of force. The strength of the induced current depends on the number of turns in that coil, the strength of the magnet, and the speed with which the magnet is moved. In other words, the magnitude of the induced electromotive force in a conductor depends on the rate of change of the magnetic flux linked to the conductor. When the magnet moves fast, the galvanometer shows high current. When the magnet moves slowly, the galvanometer shows lower current. The pointer in the galvanometer remains at zero when there is no current flowing through it. What will happen when we insert a south pole inside the coil? The deflection is in the opposite direction in the galvanometer, indicating a change of direction in the current. What will happen when the coil is moved and the bar magnet is left at rest? Let's keep the bar magnet stationary at one point near Q and move the coil towards it. The needle deflects toward the right. When we move the coil away from the magnet, the deflection of needle is towards the left. Lenz's law states that the direction of induced current always opposes the change producing it. Let us replace the moving magnet with a current-carrying coil with a greater number of turns. Let us connect another coil as shown here and name the current-carrying coil the primary coil and the coil connected to the galvanometer the secondary coil. When we switch on the primary coil, we can observe a deflection in the galvanometer connected to the secondary coil. This shows a current is induced in the secondary coil. It is obvious that without a magnet, a live primary coil can induce current in the secondary coil. This phenomenon is called electromagnetic induction. Let's summarize the various situations possible for induced current. Watch the direction of the current induced in all these cases. Moving a bar magnet with its north pole at the bottom towards the coil. Taking a bar magnet with its north pole at the bottom away from the coil. Moving a bar magnet with its south pole at the bottom towards the coil. Taking a bar magnet with its south pole at the bottom away from the coil. The induced current is high when the direction of motion of the coil is at right angles to the magnetic field. In order to discover the direction of an induced current, we can follow Fleming's right-hand rule. Stretch the thumb, forefinger and middle finger of the right hand so that they are perpendicular to each other. The forefinger indicates the direction of the magnetic field. The thumb shows the direction of the motion. The middle finger shows the direction of the induced current. Fleming's right-hand rule is also called the dynamo rule.